Hello guys, my name is Vidya and in today's video I am going to teach you how to solve numericals on modular exponentiation using Fermat's little theorem. Now in this video I have already taught you how to solve modular exponentiation using traditional method, which is by squaring method. However, when you solve the numericals on modular exponentiation using traditional method, it is quite a lengthy process. Not only manually but also it is computationally intensive for the computer. It puts a computational burden on the computer and hence we always tend to make the mathematical computation faster. So which is the other way with which you will solve it? It is using Fermat's little theorem. So if you use Fermat's little theorem, you can quickly and easily solve the numericals on modular exponentiation. In my previous video, I have already taught you the concept of Fermat's little theorem. And in this video, I've already taught you the significance of Fermat's little theorem. However, today we'll be focusing on solving the numericals of Fermat's little theorem. I request you to kindly view this video till the end so that you get a good hold on solving the numericals on modular exponentiation very easily, very fast using Fermat's little theorem. So let us now move on to our computer screen and understand the method. So let us take our first numerical, that is compute 3 raised to 4 mod 5. You can use two methods to do this. One is the traditional way of doing it and the other is using Fermat's theorem. So what is the traditional way of doing it? It is called a square method. So you first take 3 mod of 5. Now I have taught you modular arithmetic in my previous videos. You can check out my videos and understand how to solve 3 mod of 5. However, quickly I'll revise it here. Now since 3 is less than 5, 3 mod 5 remains 3. The next step is you go to square this number, that is 3 square mod 5, that is 3 mod 5 into 3 mod 5. So what is 3 mod 5 is 3. What is 3 mod 5 is 3. That is 9. And since 9 is larger than 5, you have to do mod 5 to bring it within 0 to 4. So if you do 9 mod 5, now how will you do 9 mod 5? You take the number 9 and divide it by 5. So 5 into 1 is 5 and whatever is the remainder will be your answer. So 9 mod 5 is the remainder of 9 divided by 5. So 9 mod 5 is 4. So we got 3 square mod 5 as 4. So we want 3 raised to 4 mod 5. So you have to do 3 raised to 4 mod 5 will be 3 square into 3 square mod 5. That is 3 square mod 5 into 3 square mod 5. Now 3 square mod 5 is 4 and the other 3 square mod 5 is 4. What is the answer you got? You got 16. Now 16 is a number which is larger than 5. So in order to bring 16 within the range of 0 to 4, we do mod 5. Now how do you do 16 mod 5? You take the number 16 and you divide it by 5. So 5 into 3 is 15 and the remainder is 1. So how many steps did you need to compute this? You need step 1. Then you had to compute 3 square mod 5. That is step 2. Then you had to compute 3 raised to 4 mod 5. That is step 3. So you had to do this in 3 steps. Now rather than doing these 3 steps, another way of computing 3 raised to 4 mod 5 and which is faster than the traditional method is Fermat's theorem. In Fermat's theorem, when you are given a question which is of the kind a raised to p minus 1 mod p. So in this case, p is 5 and a is 3. Now the first step is you should check if p is prime. So 5 is a prime number. And second thing that you are going to check is 3 should not be divisible by 5. Now what do you mean by this? That means if you divide 3 by 5 or if you divide 5 by 3, the answer that you get is a fractional number. That means 3 and 5 are not divisible. The only number with which 3 and 5 are divisible is 1. The only common divisor of 3 and 5 is 1 and no other number. And these two conditions are satisfied. We can now apply Fermat's theorem. Therefore, how will we solve this numerical? Since 3 raised to 5 minus 1 mod of 5, that is 3 raised to power of 4 mod 5, the answer is directly 1. So you need not solve it. You can directly say that using Fermat's theorem, since 5 is a prime number and since 3 is not divisible by 5, we can use Fermat's theorem and hence 3 raised to power of 4 mod 5 is equal to 1. So you can see that in this case, Fermat's theorem, we have not used any steps to solve the question. We have just checked if P is prime. We have checked if A is not divisible by P. And if these two conditions are satisfied, we can directly use Fermat's theorem and replace 3 raised to power of 4 mod phi as 1. So how many steps you required? You just required one step. That's it. While in traditional method, we required 3 steps. We had to compute 3 raised 3 mod phi, 3 square mod phi, 3 raised to 4 mod phi. Whereas in Fermat's theorem, you do it in one step. So Fermat's theorem basically speeds up the process of computing modular exponentiation. So let us quickly revise how did we compute 3 raised to 4 mod phi and how will we compute 3 raised to 5 mod phi. So 3 raised to 4 mod phi, you just have to check out the conditions. That is, since phi is prime number and 3 is not divisible by phi, hence using Fermat's theorem, 3 raised to 5 minus 1 mod phi, that is 3 raised to 4 mod phi, can be directly written as 1, because Fermat's theorem states that a raised to p minus 1 mod p is equal to 1. Alternatively, rather than writing a raised to p minus 1, alternate Fermat's theorem states that you can write it as a raised to p mod p is equal to a. So if we have to find 3 raised to 5 mod phi, the answer is 3. So 3 raised to power of 4 mod phi is equal to 1 using Fermat's theorem, and 3 raised to 5 mod phi is 3 using alternate Fermat's theorem. Let us check out these two questions now. If you see these two questions, they are similar, only differences. In one case, they have asked us 7 raised to 18 mod 19, and in the other case, they have asked us 7 raised to the power of 19 mod 19. Okay. If you are given a question to solve modular exponentiation, there are two ways of doing it. One is traditional method and other is using Fermat's theorem. Now, traditional method is lengthy, so we'll go for Fermat's theorem. So when you're solving using Fermat's theorem, you have to first check out that the given question is the form of a raised to p minus 1 mod p. And when does Fermat's theorem apply? Fermat's theorem applies when p is prime number and a is not divisible by p. So if these two conditions are satisfied, then you can use Fermat's theorem, which states that a raised to p minus 1 mod p is equal to 1, or you can use alternate Fermat's theorem, which says that a raised to p mod p is equal to a. Now, before that, what do you mean by a is not divisible by p? You can take a calculator and just do a divided by p. If you get a fractional number, it indicates that a is not divisible by p. That means that a and p can be divided by one and only one number, that is number 1. There is no other common divisor which a and p shares. The only common divisor which a and p shares is 1. So greatest common divisor of a and p is 1. Okay, now let us come back to this question. So we have been asked 7 raised to 18 mod 19. Okay, that is of the kind a raised to p minus 1 mod p. So what is p? P is 19. So you have to first check whether it is a prime number or not. So what are the prime numbers between 1 to 20? Prime numbers between 1 to 20 are 2, then 3, then 5, 7, 11, 13, 19. So yes, 19 is a prime number. So since 19 is a prime number and 7 is not divisible by 19. Now how do I know 7 is not divisible by 19? As I mentioned here, you take 7 divided by 19 on a calculator. If you get a fractional number, it means that you are getting some remainder after division. So 7 is not divisible by 19. That means the common divisor of 7 and 19 is only 1 and no other number. So since the common divisor is only 1, greatest common divisor is 1, 7 is not divisible by 19. Therefore, we can easily write 7 raised to p minus 1, that is 19 minus 1 mod 19, which is 7 raised to 18 mod 19. So rather than computing, you can directly use Fermat's theorem and say that 7 raised to 18 mod 19 is equal to 1. Similarly, by using alternate Fermat's theorem, you can solve 7 raised to 19 mod 19 is equal to 7. Now, why is this possible? Because P is a prime number and A is not divisible by P. Since these two conditions are satisfied, 7 raised to 18 mod 19 can be directly written as 1 and 7 raised to 19 mod 19 can be written as 7. And even if you solve this using the traditional method, you will get the same answer. Let us now check out these two questions. What is A in this case? A is 10. What is P in this case? P is 5. Now you have to check the first condition, whether P is prime or not. So is P prime? Yes, first condition is satisfied. So P is a prime number. P, which is equal to 5, is a prime number. Then you have to check out the second condition, that is 10 divisible by 5? Since 10 is divisible by 5, can you apply Fermat's theorem? No, we cannot apply Fermat's theorem. So in this particular question, 10 raised to power of 5 minus 1 mod 5, that is 10 raised to power of 4 mod 5, is not equal to 1. You cannot replace 10 raised to 4 mod 5 by 1, or for that matter you cannot use alternate Fermat's theorem, that is 10 raised to power of 5 mod 5 is not equal to 10. You cannot use Fermat's theorem or alternate Fermat's theorem to solve this question, because though P is prime number but 10 is divisible by 5. What is the condition for Fermat's theorem? 10 should not be divisible by 5. A should not be divisible by P. Now how do I know that 10 is divisible by 5? If you check the common divisors of 5 and 10, 5 and 10 can be divided by 1. 5 and 10 can be divided by 2. So the common divisors are 1 and 2. So the greatest common divisor of 5 and 10 is 2. So since 5 and 10 can be divided by some number other than 1, 5 and 10 are divisible numbers. And since they are divisible numbers, 10 raised to power of 4 mod 5 basically gives you the remainder. Whenever you do mod arithmetic, you basically get remainder. And since 10 and 5 are divisible, 10 raised to 4 mod 5, the remainder will come out to be 0. So the answer now will come out to be 0. In fact, A raised to P minus 1 mod P turns out to be 0 if A is divisible by P. Because when you do modular arithmetic, the answer is basically the remainder. And since A is divisible by P, the answer will directly be 0. Let us now check out these two questions. So the question is to compute the modular exponentiation, and it is of the kind A raised to P minus 1 mod P. The second question that is given to us is of the kind A raised to P mod P. So whenever it looks like this, immediately it will click in your mind that since it is of the kind A raised to P minus 1 mod P or A raised to P mod P, we should use Fermat's theorem or alternate Fermat's theorem. What is A? A is 3 and P is 11. So first and foremost, you have to check whether P is prime number. So what are the prime numbers from 1 to 20? It is 2, then 3, 5, 7, 11, 13, 17 and 19. So yes, 11 is a prime number. So since 11 is a prime number, and so what is the second condition you have to check? You have to check if 3 is not divisible by 11. How will you check that? You take calculator, you take number 3 and divide it by 11. And check out what is the answer. So if you get a fractional number, that means 3 is not divisible by 11. So for Fermat's theorem, we checked out the first condition that 11 is a prime number, and the second condition that 3 is not divisible by 11. Hence, you can easily apply Fermat's theorem, which says that 3 raised to power of 11 minus 1 mod 11, which is 3 raised to power of 10 mod 11, is equal to 1. Or vice versa, your alternate Fermat's theorem says that 3 raised to power of 11 mod 11 comes out to be 3. So these are your final answers. Let us now check out these questions. So again, first and foremost, you will ask yourself, is the given question of the kind A raised to P mod P, or maybe A raised to P minus 1 mod P, so that we can use Fermat's theorem or alternate Fermat's theorem. If the answer to this question is yes, it looks like A raised to P mod P, then in that case you have to check two conditions, that is 7 prime number? So yes, since 7 is a prime number, and second is you have to check whether 2 is divisible by 7. So you take a calculator and do 2 by 7. If you get fractional number, that means 2 is not divisible by 7. So since 2 is not divisible by 7, you can use Fermat's theorem or alternate Fermat theorem. So what is the answer? The answer is 2 raised to power of 7 mod 7 comes out to be 2. So this is the answer. With this, we have come to an end to today's session. I hope you understood the concept of solving numericals on modular exponentiation using Fermat's theorem. I have already taught you how to compute 2 raised to power of 7 mod 7. Now my question to you is, how would you use Fermat's theorem to compute 2 raised to power of 1000 mod 7? So kindly let me know your answer in the comment section below. And also, if you have understood the concept, if you liked the video, if the video was helpful, I would request you to kindly like, share it with your friends, post your comments and subscribe on the bell icon given below. So thank you guys. Thank you for watching this video. So see you in my next video. Take care. Stay blessed.